In this video we're going to study differentiation a little bit further than we have before, and we're going to start by looking at the chain rule. So we're going to explore the chain rule to start with some algebraic expressions. So firstly we're going to differentiate 2x plus 1 all squared with respect to x. Now if you cast your mind back to when we previously did differentiation, we would have had to expand these brackets to get 4x squared plus 4x plus 1, and then differentiate each term individually to give us 8x plus 4. However, what if we take this as a bracket as a whole? If we sort of say we're differentiating bracket squared with respect to x. So forget about the 2x plus 1 a minute, we're differentiating bracket squared with respect to x. So surely that would give you 2 times the bracket, like so. And we can then expand that bracket to get 4x plus 2. These aren't the same. What's going on? What can we do to get from that 4x plus 2 to the 8x plus 4, which we know to be correct because we've expanded the brackets and we've learned to differentiate each term separately when we studied differentiation before. So why is this method not working? Why is it we would need to multiply our answer by 2? Let's have a look at a different one, and we'll come back to this one. So very similar, we'll differentiate 5x minus 3 all squared with respect to x. So expanding will give us 25x squared minus 30x plus 9. And then differentiating each term would give us 50x minus 30. Now again, what if we had to differentiate the bracket squared? Okay, so the bracket squared differentiated is 2 times the bracket. We can expand that to get 10x minus 6. And again, the thing that we know to be correct isn't what this has given us. You can see to get from the 10x minus 6 to the 50x minus 30, we have to multiply by 5. Interesting. We'll just have a look at one more before we try and make a conjecture on this. So this time we want to differentiate 2x squared plus 1 all squared with respect to x. Again, we can expand these brackets to give us 4x to the 4 plus 4x squared plus 1, and differentiating each term separately would give us 16x cubed plus 8x. We look again, we've got the square of the bracket, let's differentiate that to give us 2 times that bracket. And expanding would give us 4x squared plus 2. And again, we don't have the thing that we believe and we know to be correct. We would need to multiply 4x squared plus 2 by 4x to give us the 16x cubed plus 8x. So what's actually going on here? We've had to adjust each of these answers. So if we look back at the first one here, what was inside the bracket was 2x plus 1. The derivative of 2x plus 1 is 2. If we look at the second one, inside the bracket was 5x minus 3. The derivative of 5x minus 3 is 5. And for the last one, inside the bracket was 2x squared plus 1, and the derivative of 2x squared plus 1 is 4x. And what we've just done is we've discovered the chain rule. So we're able to differentiate brackets using the normal rules, but we then have to multiply by the derivative of what's inside the bracket. And actually what we're doing here is we're using the chain rule. So when differentiating composite functions, we can use the chain rule, as we've seen. So if the functions f and g are defined on suitable domains, then the derivative of f of g of x is equal to the derivative of f of g of x multiplied by the derivative of g of x. So let's have a look at some more examples to see how this might work. So example 1, we want to differentiate y equals 5x plus 2 all to the power 4 with respect to x. So our solution then, the first thing that we're going to do is to identify what these functions actually are. What does the composite function actually look like? So the function f here is the part which is being raised to the power 4, and the function g of x is the 5x plus 2. So we differentiate the function f of x, so that gives us 4 multiplied by 5x plus 2 all cubed, and then we need to multiply that by the derivative of g of x, which in this case is the 5x plus 2. So the derivative of 5x plus 2 is equal to 5, so we're multiplying what we have already by 5, and that would then give us a final answer when we simplify of 20 multiplied by the cube of 5x plus 2. So just now it would be a good idea to pause the video and copying this example down before coming back for example 2. And welcome back, folks. So example 2 then, we want to differentiate y equals 1 over 5x plus 2 all cubed with respect to x. Now, we know from our knowledge of calculus before that we're unable to currently differentiate this 1 over 5x plus 2 all cubed. We need to manipulate this first so that it's y equals 5x plus 2 all to the power negative 3. And it is now ready for calculus to be performed on that expression. We should now identify what the functions f of x and g of x are. So the outside function, if you like, is the part that's being raised to the power negative 3, and the inside part, that's g of x, that is 5x plus 2. So if we start to differentiate, we'll get negative 3 multiplied by 5x plus 2, and that's all raised now to the power negative 4. And we need to multiply all of that by the derivative of 5x plus 2, which again is 5. So you'll notice that I used 5x plus 2 in the previous example as well. Now we can carry out that multiplication for the derivative to get negative 15 times 5x plus 2 all to the power negative 4. And we really should be striving to express our answers with positive exponents. So that gives us the negative of 15 all over 5x plus 2 raised to the power 4. And that's our final answer for example 2. So again, I would pause the video just now and copy this down in your notes before coming back for the next 2 examples. Welcome back, folks, and we'll do example 3 now. So a function is defined by f of x equal to the fifth root of 5x plus 2 all to the power 6 for x in the real numbers. Find f dashed of x. So our solution, again, we might realise that this f of x that we're given in the question isn't ready for calculus to be performed on it yet, so we need to re-express that as f of x being equal to 5x plus 2 all raised to the power 6 fifths. Now our outside function here, if you like, that is the part that's raised to the power 6 fifths, and the inside function that up here we were referring to as g of x, that is the 5x plus 2. So if we start to differentiate, f dashed of x is equal to 6 fifths times 5x plus 2 raised to the power a fifth. And we need to multiply by the derivative of 5x plus 2, which means we're multiplying by 5. Now the 6 fifths multiplied by 5 is 6, and we've still got our 5x plus 2 raised to the power a fifth. And we know that the power a fifth is the fifth root. So that's 6 multiplied by the fifth root of 5x plus 2. And one last time, it would be a good idea to pause the video and take this example down in your notes before coming back for example 4. And welcome back, folks. So finally, example 4, a function f is defined on a suitable domain by f of x equals the square root of 5x squared plus 2x. Find the derivative of x. And once again, you can see that this isn't quite ready to be differentiated. So we need to re-express that with a fractional index, and that's 5x squared plus 2x raised to the power a half. Now our outside function, if you like, is the part that's being raised to the power a half, and our inside part of the composite function is the 5x squared plus 2x. So we can start to differentiate and get a half multiplied by 5x squared plus 2x, all raised to the power negative a half. We then need to multiply by the derivative of 5x squared plus 2x, which is 10x plus 2. And then we need to try and simplify this expression for the derivative of f of x. So firstly, the negative power, and it's also a fractional power, so that we can re-express that part of it as 1 over 2 times the root of 5x squared plus 2x, and we've still to multiply by 10x plus 2. So we can express that on the numerator of this fraction. So the derivative of f of x is 10x plus 2 all over 2 multiplied by the root of 5x squared plus 2x, which is our final answer. So make sure you've got this example copied down in your notes, and then you can try the assigned exercise for today to practice what we've done here.